Um, our speaker today is Professor John Gammer from Wake Forest University. This semester, we have a number of speakers who were nominated for the invitation by CAM graduate students. So John was nominated by Kath Landgren, who gets to introduce him right now.
Thank you, Alex. It's my pleasure to introduce John. As Alex mentioned, he's an assistant professor in the Department of Mathematics and Statistics at Wake Forest. He also held visiting research positions at University of North Carolina, Chapel Hill, and University of Chicago. And he was a postdoctoral fellow at Brown University when I happened to be an undergrad there. And he was actually the person who first introduced me to mathematical research in general and agent-based models in particular. So he's partially responsible for me being here. And he was a great mentor then and still a great mentor. He was a long-term visitor at the Kavli Institute for Theoretical Physics, and he completed his PhD at the University of Arizona. John works on problems in areas of calculus of variations, dynamical systems, and stochastic differential equations, and he's actively collaborated with researchers within applied mathematics as well as across disciplines. And now let us find out why lettuce is so wrinkly.
Thank you, Kath. Thank you for the really nice introduction. And thank you all for being here. I know this is kind of awkward times, and I'm really happy that Cornell is keeping their Colloquium series going. I know personally that's very difficult. So thank you again for having me here. One thing I want to comment on, just in case it happens, we had a tornado come through Winston-Salem the other day. Power went out, and so my wireless has been fluctuating. Every once in a while I just get dropped. So don't feel that I'm just running away from the Colloquium. I will be back in about 5 minutes whenever the wireless resets. Okay, so what I want to talk about, I mean, I think I gave a slightly different title, but this is the kind of lowbrow title. It's just basically, why is lettuce wrinkly? And before I get into it, I'm just going to acknowledge a little bit about my collaborators, because I always forget to do this if I put this at the end. So this work did start in my PhD with Shankar Venkatraramani at the University of Arizona. And that work was in collaboration with Eran Sharon, who's an experimental physicist at the Hebrew University of Israel. And when I was a postdoc, I began working on other problems, but then towards the end of my postdoc, I came back to this problem with some kind of new ideas. And I worked with Toby Shearman, who is now working at Conversant. It's a company in Chicago. Max Rezik is actually my former master's student, who's now a PhD student at University of Arizona. And some of this work is actually in collaboration with a really sharp undergraduate student who spent a summer with me. The past summer 2019, he worked with me on aspects of this problem. And so my funding, I was on sabbatical last year, so even though this has nothing to do with climate, part of my funding comes from the Mathematics Climate Research Network, the American Institute of Mathematics, and I had generous funding from the University of Chicago. Okay, so the question of why is lettuce so wrinkly, I mean, it's just kind of, it's an interesting question in its own right. Like, you can look, if you look at common lettuce that you would see in a grocery store, you do see this really interesting structure. And glibly, you might say, oh, it has hyperbolic geometry. And that's true. It's a saddle everywhere. But if you look near the edge, you can see this beautiful wrinkling pattern. And you might zoom in a little bit, and it looks almost fractal-like. So it's just a natural question. Why in the world would this system form these fractal-like shapes? Is there a mechanistic reason? So you can get a lot of teleological answers. You might ask somebody, you know, I get this sometimes when I give this talk, you know, well, I think lettuce is wrinkly because that helps capture water and sunlight the best. Okay, that might be true, but what is the underlying mechanisms that would actually drive the system to form these type of patterns? So by the end of the talk, I'm hoping to give not a complete understanding. I can't tell you exactly why these particular shapes, but hopefully a description of how these shapes arise as natural local minimizers of a variational problem. So There you go. So here's just some other pictures of this. So this is on the left, just a leaf. You see some periodic rippling in the upper middle. There's this is an Echeveria plant. I took a picture of this at the San Diego Zoo, and you see these type of patterns in flowers, in marine life. So these are actually sea slugs. You again see this hyperbolic geometry. Okay. So I like this quote a lot. So the quote is, outside our boxes, nature teems with frilly crenellated forms, from the fluted surfaces of lettuce and fungi to the frilled skirts of sea slugs and the gorgeous undulations of corals. These organisms are biological manifestations of what we call hyperbolic geometry. And so here's some beautiful crochet models of hyperbolic geometry. And again, just by some simple rules in crocheting, you can replicate what we see in marine life. So, okay, so a little bit of math. I do want to have like a quantitative rule, so for why we can understand how these patterns might arise in nature. And the simple idea is we're going to model growth as local distortions of lengths. So in this cartoon diagram, I've just drawn a grid, and imagine I want to measure the length between the 2 points. Okay. And what we tell our calculus students is, okay, you parameterize this curve and you do an arc length integral. Great. So, however, if I think about an object that's grown, one way to model this is to think about the growth as locally distorting the differential distance between points. And so the way I think about growth is, if I put on a UV coordinate system on this disk, I can think about the growth itself as slightly distorting Pythagorean's theorem locally. Okay, and so I can capture this in these components of the arc length form, and I can encode that in a metric I'm going to call G. So this is really, you can think of this as a tensor or a matrix that depends on spatial coordinates, but this is capturing the growth at every point in the disk. Okay. So, and then you can do the only modification to the arc length integral is this tensor acting on these vectors. Okay. So in a grown object, this is how I should measure length between points. So the response of the sheet to this local growth, we're going to model as a deformation of the surface. So I can imagine there's just some mapping that takes the grid that I have abstractly in my mind, and I map it into a distorted shape, and I can measure the length of the distorted curve. And if I compute that, what I get is this squared of the derivatives. So this is known as the deformation gradients, this deformation gradient squared. But the point is, if I have a surface, I can measure lengths on that surface. And the way to do this integral is encoded entirely in terms of this quantity, this metric tensor. Okay. And so this is the rough idea of non-Euclidean elasticity: is the G is some known quantity given by the growth profile, and I want to find a surface that matches it. And any discrepancy from matching that growth profile is what I'm going to call a strain tensor. Okay. And if we think of this geometrically, this is analogous to the classic isometric immersion problem in differential geometry. If I give you a growth profile or I give you a Riemannian metric, can you find a surface that matches it? Okay. So that's the rough idea of how you could model growth, is find a shape that models this growth profile. Okay. So this problem is geometric, and the point of this slide is to show that the way I'm thinking about growth is, this is an intrinsic quantity on the sheet itself. So in other words, if I take an object, so in the upper left, there's just a picture of a proof of Pythagorean theorem. And now I imagine just warping that image without stretching it. So really just bending it. Then the length between points is not going to change. And so this notion of matching a growth profile is an intrinsic quantity on the surface, in the sense that locally, by trying to match the surface, is entirely encoded in the local geometry in that metric G. However, the bending of the surface itself is extrinsic. So what I mean by this is, if you actually do bend a sheet, you are putting curvatures in that sheet, and the residual stress that you feel from curving something comes from the extrinsic quantity, namely the principal curvatures of the sheet. So the interesting thing, though, is this notion of Gaussian curvature, another measure of curvature, which is actually intrinsic to the sheet. And I guess it's been so long, maybe this isn't as surprising as it once was, but this is supposedly one of Gauss's most profound discoveries, and one of the most things he was most pleased about was discovering that you could measure, in some sense, the curvature of a surface by intrinsic quantities. And so this is a cartoon diagram of how I think about Gaussian curvature. And one way is you could define that as a determinant, but kind of intuitively to me, what you're really doing is measuring the discrepancy of circumferences of circles. So what I mean by this is, if I do something like let's say I tied a rope around myself, I put a pole down, and I walked 10 meters out, and I formed a circle. And if I measure the circumference of the circle I formed, because I'm on the Earth, it's going to be actually a little bit lower than 2 pi r. And if instead I was on a saddle, my circumference would be greater than 2 pi r. And so what Gauss did was he found that you could actually compute the Gaussian curvature by taking the limit of this discrepancy. And so Gaussian curvature, to me, is a notion of how distorted local circles are from being flat. And you can measure that through their circumferences. Okay. So the reason I bring this up, though, in terms of coming back to the applied problem I'm looking at, is you could actually think about modeling then growth and Gaussian curvature is the same. So my collaborator, Aran, in his laboratory, what he is very interested in doing is creating programmable gels. And so using a Healy-Shaw setup, what he can do is vary the polymer concentration of these gel discs. He can put them in a hot water bath and they activate. And the point is, by varying the concentration, the periphery of these discs are going to grow at different rates. And so by doing that, he can put in Gaussian curvature into a sheet. And when it gets activated, it morphs. And so this is a reversible process. So if he, I think he cools the liquid here, it'll go back to its original shape. The interesting thing, it doesn't have the exact same dynamic pathway. But you can see the effect of putting this local growth factor into the sheet in its shape. Okay. So other collaborator, Chris Santangelo, is also using a technique in which he takes a sheet and actually puts in these little dots into the sheet, which can be activated by, let's see, so he did this by like what he calls gel lithography, where he basically puts this in a printer where you can put in these little dots and then put it in a warm water bath, and these little dots swell at different rates. And by doing this, you can put curvature into the sheet. And of course, his idea is, can I use this? Like, if I can put down these dots in a controlled way, can I morph an object into a desired shape? So these are more pictures from Aron's experiments. He can get all different types of geometries out of these sheets. So you have, of course, spherical geometry. You have hyperbolic shapes, which have which are surfaces of revolution, but you also get these kind of saddle shapes as well. And then you get something which is a mix of positive and negative Gaussian curvature. Okay, so what I want to give a taste of, though, is before I mentioned that, yes, we're thinking of growth as a Riemannian metric. And the naive idea would be the sheet adapts its shape to best match that Riemannian metric. But I want to think about this from a variational perspective. So again, I'm thinking about some known geometry, something like a disk, like in Aron's experiment. And we're putting on some growth profile, and the object deforms into space. And we're going to model the actual shape taken by the surface to be a minimizer of an elastic energy. So this type of energy has two components to it. The first term is a stretching term. So this functional penalizes deviations from the growth profile. And then there's this weak effect from bending, where here T is the thickness of the sheet. And so this kind of captures the multiple scales in this problem, in the sense that we know for a very thin object, if I try to like pull a leaf, it's very hard. It resists stretching. But the bending effect is very easy. You can just push on a leaf and it'll bend a little bit downward. So this captures the scales in the problem. And it's a tricky proof, but what you can show rigorously is that in the thickness going to zero limit, you can, minimizers of this functional converge to deformations which have zero stretching. So they actually solve this geometric problem, but that minimize the bending energy. And within this class of functions, this just reduces to minimizing the Willmore functional, essentially. Okay. So in some sense, this seems very clean as a mathematical problem. Solve this isometric immersion problem. If I can think of all the possible solutions to this PDE, just optimize over the Willmore functional. Okay. But there's a problem that is kind of at the forefront of everything I'm going to talk about from now on. I'm not going to give you the very precise theorem, but the rough idea is that when you try to isometrically immerse the hyperbolic plane, or you try to solve this PDE, if you restrict yourself to smooth solutions, there's a known problem that given a smooth solution, you can only solve this problem for a finite size disk. And so classically, you can see this if you open up any differential geometry book. They will give you surfaces that have hyperbolic geometry. And so the leftmost one is the most famous one. This is the pseudosphere. And if I look at this picture, it has this rim on it. And that's precisely where the curvatures in the sheet diverge. So there's a singularity in the sheet. And there's a lot more exotic surfaces that you can generate. There's breather surface, Kuhn surface, etc. But all of these will always have these defects. And the natural question is, first, like, we know if I try to solve this with smooth solutions, I'm going to have to deal with these defects. Second, these sheets don't match what we observe experimentally. So we might think, okay, the experiments and our model are completely off base. That's a possibility. But they can take very detailed calculations of these sheets, and they do seem to be legitimate isometric immersions. So this was supposed to play a little bit later, but so how life solves this problem, or how does nature solve this problem? Well, nature doesn't really care about our mathematical limitations. So it will find a way. And so I threw this picture in, and I gave a talk on this a week ago to undergraduates and graduate students. And I asked them if they knew who Ian Malcolm was or where this picture is from. And it was just stone cold silence. So does anybody feel brave enough to say where this is from?
Jurassic Park.
Oh, good job. Good job. This makes me very happy. Okay, good. Yeah, so this is Jurassic Park, and Ian Malcolm actually, well, I looked up to him when I was a kid as what a mathematician should be. But anyway, so.
Boy, were you off.
Yeah, I know. But I like this quote anyway. So yeah, I mean, like, even though we have these surfaces with these singularities, nature does something different. And so why does it do it? And how does it select these isometries? Okay, so let me give you some more experimental observations on this, so that are a little bit more precise. And the first one on the upper left, these are Crochet models of the hyperbolic plane. And what I'm thinking about for this kind of simple model is it's a fixed thickness and fixed Gaussian curvature, and you're growing the radius. And so what happens is it starts off exactly like you'd expect, a saddle shape. And then as you grow, you see more complex morphologies emerging. And as you continue to grow, you see more complexity set in. Okay, this seems to actually somewhat line up with the theoretical results. That is, as the disks grow, they're going to get more convoluted because of that singular edge. Okay. A second experiment, this is the one done by Iran, is quite surprising in that what he's doing here is fixing the size of the domain and decreasing the thickness. And in doing that, he's relaxing and making the bending energy weaker and weaker. And so the previous theorem I quoted was that as thickness goes to 0, this is supposed to select a particular morphology. But what we're seeing is actually a buckling behavior with decreasing thickness in the more complex geometries. And then towards the end of the talk, I'll talk about this experiment in more detail. But he also did work on torn elastic sheets in which he just took different material. And if you put a tear along a plastic sheet and you look at the boundary, you will see complex morphologies emerge depending upon the decay rate of the growth process. So for fast decay, you get these single wavelength profiles, and for slower decay, you can emerge these fractal patterns. Okay. And again, this is something similar to what we see at the edge of a leaf. Okay. So again, the question is, why do these patterns emerge? Why these complicated fractals? Okay. So let me give you a little bit of the math background on this. I don't want to spend too long on this. So the original impetus for this work goes back to Michael Marder and Sweeney at Texas, and they were interested in just like, why do flowers have the geometries that they do? And they wrote a paper on this, and they showed that the smooth solutions are going to consist of helices, saddles, or some kind of periodic profiles, but not fractal-like. And one of the takeaways from their work is that you'll get these saddles are these pseudospherical-like shapes, but because of the singularity that naturally arises, the variational problem can't capture the physics past these singularities. Okay. But there are numerical experiments that contradict this, where they did finite element simulations, which do seem to replicate these fractal-like patterns. And Maha was involved in some of this work in the late aughts, in which he, again, looked at the Fabel-Karman equations for this problem, and he showed, no way, you shouldn't get fractals. If I look for solutions to this, doing kind of what we know, looking for Fourier modes or whatever, you should get these periodic profiles. Okay. And then there's some technical results using gamma limits by Marta Lewica and Reza Paksad, which shows, yes, you can rigorously show in this model, in the thickness going to zero limit, you will get an isometry. But there's a key point they make. It's a W22 isometry, so not necessarily smooth. And in fact, so this is the work I did for my PhD, was I constructed non-smooth solutions to this problem that more closely replicated what we observed experimentally. It still didn't close the gap of saying, okay, why do fractal-like patterns emerge? But I was able to construct piecewise smooth solutions that are in fact the right regularity that at least qualitatively replicate some of the experiments. Okay. Okay, so let me walk through a little bit about how this is done, because it's not a standard process. So the idea I'm going to present first is, okay, if I want to try to solve this variational problem, a lot of times you just make a good guess and minimize over that class of guesses.
Seems like we lost him.
Slide up here just to show that these are the underlying PDE.
John, I'm sorry, we lost you for a second. And so as a result, we missed part of your explanation. You might want to unroll to the beginning of this slide.
Can I ask a quick question while we're paused? So the question is, the motivating examples, several that you showed, have material effects, for instance, tearing the plastic. So there's this question of what's elastic and what is also nonlinear in its material response, and how do these affect the deformation patterns that you're observing? He might have vanished completely.
I'm back.
I think he missed your question, Chris.
Okay. So yes, I'm sorry. It just seemed like a good time to ask it. But some of the motivating examples would indicate that there may be non-elastic material response, specifically the tearing of the thin plastic sheet that you showed, and also the crochets. And so, so we're restricting attention really to just elastic systems, yes, and some of these may be slightly different than what the motivating examples you showed would indicate.
Yeah, this is an excellent point, especially for the tearing in particular. That is really truly a plastic deformation. And so you're exactly correct. Like, if I really want to model that tearing process, I really should do it as a dynamic process incorporating plasticity. And you're entirely correct. Like, it's a little bit jumping the gun. My perspective is we tear it, and that plastic deformation, I'm going to model as growth in some sense. And whether or not that's correct, it's incredible. It's a very good point. And in fact, the way we measure that metric was a little bit assuming what we want to prove. We take that torn profile and then we measure locally the change in coordinates. And we're using that to generate the growth profile. So in that one, in that torn plastic sheet, you're exactly right. That is a weakness of that experiment, in that you could say, is it the plasticity that's really driving it? Or is it the fact that I put residual stresses in this and now it's going to relax into this wrinkled shape? So that was actually a precursor to that using the gel discs. So in the gel discs, we know that's more like a polymer network, and we kind of understand the elasticity better there. So we were really reinforcing, okay, let's do this more carefully. Now let's actually program in the growth itself beforehand and not measure it after the experiment, right? And then allow it to relax. But you're right, there's some discrepancy in the modeling versus the actual what's really physically going on.
Okay, I just wanted to just sort of clarify that, but thank you so much. I appreciate it.
No, it's an excellent point. Other questions? Okay, so okay, so what I was going to do is I can rescale this in this dimensionless radius, and I wrote down these PDEs just because I wanted to emphasize that they're complicated, and I actually don't want to solve them. But I wanted to point out, like, even at this level, when I take this small dimensionless parameter, you get this coupled system of fourth order differential equations with, in some sense, the Gaussian curvature serving as a source term. And then the boundary conditions are also complicated. So, and a lot of times naively, if you mention you're doing elasticity, people will think maybe working at this level of the equations, and I'm going to introduce this small parameter, so maybe we could do matched asymptotics on this problem. And you can, but you need a good guess for the solution in the first place. And so that's kind of the chicken and the egg with these equations anyway. So
Can I ask what is phi?
oh, thank you. That's the area stress potential.
Okay.
Yeah. So it's not on this, but that is exactly the stress potential for this problem. Only in the in-plane coordinates, though. So it's not the, that's it. This is all the two-dimensional geometry from this point. Everything in the out-of-plane displacement is put into this eta term. Everything else are the in-plane terms. And this is the kind of the typical von Karman ansatz where you do order epsilon squared in plane and order epsilon out of plane. And to first order, you can make the strain terms vanish, so you get to these equations. So. Okay, but I do want to point out you can fiddle with these equations, and what you do get for an isometry is you actually get a very nice solvability condition. Although this is a Monge-Ampere PDE, so it's not easy to solve, it's easy to write down, but that's what you get. And so writing this out a little bit more explicitly, this is the PDE that's going to govern the isometries, at least in this asymptotic limit. Okay. So to solve this thing, you just do the naive thing. I mean, it's second order and there's a constant on the right-hand side, so you guess it's a quadratic. And you can do that. And you get a whole one parameter family of solutions. And I wrote it in this way with this parameter A. The reason I did that, though, is if I look at these solutions, these are all going to be saddle shapes. I mean, it's a quadratic, right? But there's something really interesting that happens is these shapes have two straight lines through the origin. And at the time, I just wanted to make this match experiment. So what I did was I took out a piece of this and periodically reflected it. And I got a 3-wave. I said, great, this matches experimentally. And maybe what I did is a bit odd, it's a bit ad hoc, but it does match what Iran's experiments have shown us. And I do want to point out that this is a valid W22 solution to this PDE. It's clearly not smooth, but its derivative will be continuous across these lines where I'm reflecting. So the interesting thing, and this is I think a funny thing about research is, so the prior thing was what I did in my PhD. And it wasn't until about 6 years later or so that I realized, wait, the origin doesn't matter. You could put this type of defect anywhere on the sheet. And so on the left-hand side, what I'm showing you is the local coordinate system on these surfaces. And it's ruled by entirely straight lines. And so when I did this reflection, this is what happens to the coordinate system, and you could look straight down on it. And in some sense, this has an interesting topology in its own right. So just by calculating the rotation of these normal, so these are the normal across around the origin, you can get it a notion of like an index of these type of defects. And so this would be like an index -1. This would be like an index negative well, I think of this as like a -1. So I'd really call this one like a -4, given how many times it rotates around. Okay, but the thing that took a while to realize is, wait, even for this simple geometry, what I can do is excise a region and take other solutions to the Monge-Ampere equation and glue them in to this surface. And then once I did that at this point, I can do it at other points just as easily. And so this gives me a construction where I can create a self-similar surface. That's nice. That's getting closer to what we observe experimentally. And so you can look at the profile and it does look like a leaf. Okay. But fortunately, you can do all the energetics for this problem. And it's quite easy to prove that in the small slopes regime, or this regime where I Taylor expanded in this small parameter epsilon, this saddle shape is always going to be the local minimum. Okay. So what we did then was decide, okay, we really need to look at the full geometry of this problem. We can't just get away with this small slopes approximation. We really need to look at the effects of this hyperbolic plane, in particular, the existence of these singular edges. So there's a cute trick you can do with the hyperbolic plane, and that it's got a very nice parameterization where you can encode all of the geometric information in terms of the angle between the asymptotic coordinates. And if you do this, the principal curvatures can be put in terms of this angle. And so you can look at the leftmost picture and you can see exactly how the singularity arises in terms of these angles. So when the angle is 0 or pi, they're completely tangent, and that's exactly where you get this singular rim. And there's kind of more magic involved in these equations that you can actually show that this angle satisfies the sine coordinate equation. So it's amazing. You get this very well-studied PDE from which you can generate surfaces. And all of this geometric information is encoded in the solution to this PDE. So, and then you could write the bending energy entirely in terms of this angle. Okay, so the interesting thing then is you could use this framework to actually minimize this problem. So I can look at minimizing the bending energy over solutions to the sine Gordon equation. And this is what we did, and at least numerically, you could show that solutions are going to have this type of symmetry of their solutions. And plugging this in, I mean, it's kind of more magical. You get just the equation for a pendulum. So solutions to a pendulum are going to generate smooth isometries, which are going to correspond to surfaces of revolution. So you can just draw a phase portrait and minimize over this phase portrait, and you get this solution here. And this is going to be the minimizer over the smooth surfaces. Okay. The problem is, again, these don't match experiment.
We seem to be having another connectivity issue. Let's hope that the speaker will reemerge. Okay, at least the mouse is back. I think one of the things we will try in the future, perhaps, is to ask the speakers to provide a copy of the slides ahead of time, so that if we experience connectivity issues, we can at least try to pick up each one of us on our own using their slides. And there is John again.
I'm back. Sorry about that. Okay. I don't know where I disappeared, so I hope I wasn't talking to myself for too long.
Perhaps a slide earlier.
Okay, so let me figure out how to make the slide go back. There we go. So I just want to comment a little bit about, I just put up this theorem that really does quantify the growth of smooth solutions to this equation, how they grow exponentially with the radius of the disk. Okay, so what I wanted to do, though, was use this framework of solving the sine-Gordon equation to generate isometries that replicated what I did with the small slopes. So in particular, you can look for special solutions to the sine-Gordon equation by looking for similarity solutions. And in particular, we were looking for solutions that had these straight lines through the origin. And so if you do this, you get this beautiful embedding of the hyperbolic plane that has these two straight asymptotic lines. And the point is, I can control that angle between those lines. So I can replicate exactly what I did before by making periodic reflections. Okay. So this is nice because at the level, I can analyze solutions to the sine-Gordon equation, and I can extract quantitative information. And so by doing this construction, I do get these piecewise smooth immersions. And I can now see the price I'm paying energetically. So what I've done in the upper left, this is the two-wave solution. And you can see with growing size, you eventually begin to reach points where the bending energy begins diverging. And so a naive thing would be, okay, why don't I switch to the three-wave solution? The price will be I'll pay a bit at the origin, but I can go a little bit further. And then you can kind of replicate this process. And this little ring is supposed to represent where the Monge-Ampere equations or the small slopes approximation was accurate. Okay. So this is just a cartoon movie of this bifurcation with the domain size where we see these singularities begin to form. And here I'm just switching by hand. There's no dynamics in this. I'm more or less just having the geometry kind of break its symmetry a little bit and switch to the more energetically preferable shapes. And you can, again, do this numerically. So this plot is these colored curves are the energies of these different periodic profiles versus the energy of the smooth solutions. And you can see a clear transition where the piecewise smooth solutions have lower energy. Okay. And at least they roughly replicate what we see experimentally for small domains. Okay, but what would be nice is if I could replicate what I did in the small slopes approximation, where again, what I'm doing in this construction is I'm putting down a point at the origin and I'm reflecting. So I'm doing this thing very constructively by hand. I'm saying this is how you do it. And I'm using the fact that there are straight lines through the origin to do these periodic reflections. So the way we extended what I did by moving those singularities is a little bit more challenging in the full geometric problem. The key observation is it's not the fact that we had straight lines to the origin, is that these were what are known as asymptotic lines. And along an asymptotic line, the rotation of the tangent plane is entirely dictated by the Gaussian curvature. So the reason this is important is if I'm trying to glue together two pieces of the hyperbolic plane together, I need their tangent planes to match, otherwise they have infinite energy. And so, but the fact that they rotate at the same rate means that as long as I glue these two pieces together and I have, they rotate at the rate dictated by the Gaussian curvature, I can glue together pieces of the hyperbolic plane. And technically, to do this, you have to solve the system of PDEs. And really what I'm doing is using characteristic data to glue these together. Okay. This is very challenging. And what we ended up doing is using discrete geometry instead, where you imagine putting down a bunch of quadrilaterals, and I'm going to try to piece together along the quadrilaterals. This is nice because you get a very simple discrete system to solve. And as long as you nucleate it with initial data, you can fill out the surface. Okay. So this is my colleague, Toby. I think he hates when I use this picture, so it's in every talk. But this is his construction. So this is what he was able to do. He's an excellent numerical analyst. He was able to patch these things together to generate a representation of these surfaces in real space. And his work, I mean, he calls it hyperbolic origami. It's very generic. It's not restricted to just the hyperbolic plane. Anything with negative Gaussian curvature, all you need is some kind of topological skeleton for what type of grid you want to use, and some rules for gluing together along the lines. And with some geometric data, so that's your Gaussian curvature, out comes a surface. And so here's a movie of this surface. And to me, this is just amazing how well it replicates what some of the patterns we see in nature. So you got to be careful in any talk, right? We cherry pick the movies and the pictures that we want to show. But in a lot of the patterns for the hyperbolic plane that we actually observe in nature, this does a really good job of replicating the process of why we see this kind of undulations in the sheet. But more importantly, there's a quantitative understanding of this as well. So previously, I presented this result in which we were able to prove that for smooth solutions, the energy grows exponentially in the radius. But through this construction, you can put down these points generically. So you can give an ansatz in which you get a drastically lower amount of energy by putting in these defects. So these fractals are these fractal-like shapes naturally arise as the local minimizers. So the point is there's an energy gap between these two types of solutions. Okay. So I'm running out of time because I lost a little bit. But I do want to point out this, this is a blurry image of this, but this is the quantitative, this is from the numerics that do show these branch solutions have drastically lower energy than their smooth solutions. But I want to end with trying to answer the question of why leaves are so wrinkly. So in the previous experiments, I was just talking about constant negative Gaussian curvature. So you can do this for more geometric or more generic shapes. So here I'm just trying to replicate Aron's experiment on the torn elastic sheet. So I put in a growth profile with some algebraic decay. And again, smooth solutions exist. Okay. And to remind you, this is what the experimental data looks like. So it's kind of the exact same framework that we did before. You can make an ansatz and you can derive a Monge-Ampere type equation. And the interesting thing is you can also solve this equation explicitly. You make the natural separation of variables ansatz. You will get a Hamiltonian system. So that will at least give us some kind of periodic solutions. And like what we did in the previous case, you have these lines of inflection along which you can make periodic reflections to get this rippling pattern. So, but what's different about a leaf is the Gaussian curvature isn't uniform through the sheet. And if I imagine like cutting the edge of a leaf, what you'll see is that it wants to form circles of different radius throughout the sheet, depending where the Gaussian curvature is concentrated. And this has the effect of, within this class of solutions I presented, as there are different wavelengths that the sheet itself wants to adopt. There's a global wavelength, which is if I just plug in this solution, integrate, and minimize, that would give me one periodic pattern. But there's also a local wavelength. At each part of the sheet, it wants to have a different wavelength. So how do you patch those together? And so that is exactly what we did with replicating what we did before, is you can introduce branch points into the sheet. And you follow the same framework of gluing these together along asymptotic lines. And the trigger for when you introduce branch points, you just measure as a local disparity between the principal curvatures. And so on the contour plot, it's quite easy to see. I'm coloring this by the local bending content. So when the energy gets really concentrated, you put in a branch point and you lower the energy. Okay. And if you plot the surface, it looks fractal-like. And we did do the exact same type of analysis where we compared smooth solutions to these fractal-like patterns. And there is a clear bifurcation and a clearly different scaling law. This is on a log scale, so you can, it's quite easy to see that square root law versus the standard linear exponential growth. So in this case, at least, like the answer of like why lettuce is so wrinkly is the geometry of the hyperbolic plane. It naturally is going to introduce singularities where the bending energy gets very large. But with hyperbolic geometry is very floppy in the sense that you could put in little local defects. And those local defects will allow the sheet to drastically lower that bending energy locally. So this is kind of a pie in the sky project, but you can imagine this is actually a nice mechanism for something like a marine animal to actually swim underwater. But they have a very floppy body. I mean, there's no bones in it. But the fact that these branch points are very low energy to introduce can allow this object or this animal to morph its morphology to swim through the water. So anyway, so in summary, like why we think lettuce is so wrinkly. I mean, the key point is it's a balance between this rigorous mathematical theorem that says if you try to immerse something, a hyperbolic geometry, smoothly in Euclidean space, you will get points in which the principal curvatures diverge. And however, you can put in these branch points are very low energy defects. It's kind of unfortunate that we're calling them defects. Even classically in elasticity, defects mean something very dramatic has happened to the sheet, like you put a crease in there or something, and energy is concentrated along the defects. This is a new phenomenon in these type of multi-scale variational problems, in that it's actually the opposite. These points where the function is not smooth actually disperse the energy, not concentrate it. And the technical result is these low energy minimizers exist in a completely different function space. And while they both satisfy the same PDE, the smooth solutions these low energy minimizers are not dense in the space of these smooth solutions. So this has consequences for things like numerical simulations, in which you want to do something like build a finite element simulation that would model these sheets. That's grounded on some theory that you're approximating these by smooth solutions. But the fact that these low energy minimizers exist in completely different function space means you're going to have to build your finite element solvers very carefully to account for these type of defects. And I think the correct way to view it is really through the discrete geometric viewpoint, not this type of, I think because every time we try to do the PDE work, as we normally would, it's very, the hyperbolic PDEs are naturally ill-posed in the sense that you will get diverging characteristics very quickly. So anyway, I just want to leave this one last video of this morphing disk that's from one of my friends, Robin, who made this for me. So thank you all for listening.
Thank you very much. Let's thank the speaker. You're welcome to upload either through the Zoom feature or to unmute yourself and do it in reality with me. We do have time for a few questions, and after that, there will be a reception in Camp Gathertown. Erika, if you could please post a link. Oh, you just did in the chat window. So we hope to see many of you there. And now time for a few questions.
So I actually have a question again. Sorry, this is not exactly my area, so forgive me if it's sort of a little bit off the mark. But I understood you to be saying in the beginning that the deformation gradient was selected as a way to construct a metric tensor based on sort of this zero strain idea. And so and then when I looked at your leaf slide, you did this beautiful analogy to what we would do in experimental mechanics, where you do a residual stress test, where you segment the piece and it curled, and we would, yeah. And so it just puzzled me. It seems like there's a locked-in strain field, and that seems a little bit at odds with everything that I was under the impression of when I was looking at the talk.
Yes, this is an excellent question and an excellent point. Is that the way I've kind of posed this is using classic elastic theory, which is you have this in-plane strain, and then if you match it, there's no residual stresses. So one of the things that's different, this is not a shell theory that's saying, okay, I have a curved object with an intrinsic Riemannian metric that I'm going to measure strains from. It's actually an abstract Riemannian manifold that I'm going to measure strains from. And it's really a three-dimensional Riemannian metric. And so really the true framework is I start with the three-dimensional Riemannian metric, which encodes growth, and I measure the deformation gradient from R3 to R3. And what I'm doing though is I'm really put this in a very specific geometry where I'm imagining layers of the sheet which are uniform through the thickness, and I'm expanding through that. So that bending energy, which relied on the principal curvatures, that is the term that's actually capturing the residual stresses. And it's the difference between Euclidean versus non-Euclidean geometry. So Euclidean geometry, I can make the in-plane strain tensor and the out-of-plane strain tensor both go to zero by just looking at the flat surface. Mm-hmm. But for non-Euclidean geometries, you can't have both equal to zero at the same time. And so that, at least at the heuristic level, is what's the difference between non-Euclidean geometries. You can't get away from the residual strains. And so that makes the definition of like a reference surface, or I forget what they call it, like but the one you're measuring the strains from, right?
Neutral surface.
It doesn't actually exist in Euclidean space. And that's why it's somewhat bizarre. But so when those earlier drawings, I was drawing that flat disk, that's still kind of wrong. It's really an abstract Riemannian manifold that I'm referencing all my strains.
Yeah, your bending energy wants it to be straight, but it can't.
That's exactly right. It can't be straight and have zero stretching. That's right.
Can you, speaking of which, well, first, can I ask your branch point business that you call it a branch point construction?
Yeah.
Can you have infinite refinement on that?
You can. There's no reason not to. Well, there is a reason not to. There's a cutoff in the energy, though. So one of the things, it's actually clear from this slide where I did the Chebyshev nets. So this slide, it's not quite the same for surfaces that don't have constant Gaussian curvature, but this angle dictates the energy. And so what happens in these branch points is I have a very wide angle near the singularity. It's essentially becoming pi. And so one of these curvatures is diverging, so I trisect it. And now I have 3 angles of pi over 3, which is a lot less. And then each one of those solutions is going to begin diverging as well. And so then I trisect it. But the problem is if I keep doing this trisection, I'm getting smaller and smaller angles. So I'm getting closer to the opposite end where there's 0, right? So there is a price to pay. There is a cutoff that you don't want to refine too much.
Okay, good. Can you go back to your, it's one of your early slides with your energy?
Yeah.
You know, it's at the very beginning.
Yep.
So I would argue that what you're really doing is constraining the strain tensor to match with the metric tensor. That's really not an elasticity law. That's actually a constraint. And so, and then what that would do when you go, I know you didn't solve the PDE equations, but if you did, the Lagrange multipliers that correspond to that guy would actually show up in your PDEs.
Yes, you can actually exactly view this problem that way. And
because that's really not a stretching energy.
Well, I would disagree that this is a stretching energy. I mean,
well, it's not. I mean, you should have at least 2 elastic constants.
I see your point. Yeah, yes. I assumed this was.
This is a mathematician stretching energy.
It totally is. Yeah, I should put the assumptions that like Poisson's ratio is a half. It's.
But I think it's much cleaner if you just view this as your constraint, and then you're minimizing bending energy based on that constraint.
It's hard. You have to. The thing is, you have to prove that, and that wasn't clear. This was actually the starting point. Is like from when I started on this, it wasn't clear that you could just set 0 stretching energy and then minimize over bending because of this existence of this singular edge. And it was kind of a folklore in the physics community that, oh, there are no isometries with finite bending energy. So really the stretching term can't go to 0. So the original thought process was that, oh, there must be some scaling between these two. And so the stretching energy is going to scale with some power, the thickness and the bending is going to scale with the same or similar power so that they all give you the similar contribution. And this was the obsession from the physics community, was to try to get that scaling exactly right.
Mm-hmm.
And it is a rigorous proof to show that you have to use gamma limits carefully to show as you can take the thickness going to 0 limit.
And is it totally dependent on your definition of stretching energy, or can you?
No. So this is, you really do start with a stretching energy that measures the full 3-dimensional Riemannian metric, and you just, I see your point. It is.
No, but I want to see real. I want to see real elasticity there instead.
Yeah. So you're exactly right. That you want to put in something with the elastic parameters in there, and the proof that Marta did was for a generic norm. So you could think of that norm as having those elastic parameters built in. And what we end up doing is like, okay, we can't analyze this thing for a really hard norm. Let's take something that's equivalent. But you're exactly right. Like you could say that, yeah, what I've done, I haven't included Poisson's ratio or de Young's modulus into this problem. And those should be built in. And you're right. And I did do this in a different paper where, so you can factor out the Young's modulus. It doesn't matter in terms of minimizers. The Poisson ratio does matter, actually. There are boundary layer effects in which that term will give you different phenomena.
So I apologize. I will cut in at this point since we are a bit over time at this point. I would suggest to continue the conversation at the Gather Town.
Sure.
And we should thank the speaker again. And
very nice stuff.
Yeah, thank you.
Thank you very much.
Thank you so much.
Thanks all.